Okay, so when we look at this one, our a sub n, what's inside here, and then what we're going to compare it to are the dominant pieces. So the dominant piece of the numerator is 2n. And then down here, think about if you multiplied that through n to the fourth would be the dominant piece. And then we can just eliminate an n from the top and bottom. So this is really what we're comparing it to. And when I try to compare my a sub n and b sub n, I want to try to figure out which one's going to be larger. And here, it looks like it could be kind of either. It's kind of hard to tell, because this one we're adding 5, which is larger than adding 1. This one we're squaring. So I kind of feel like this denominator is going to overpower it, which is going to make it less than or equal to. But I'm not positive, and if I'm not positive, I might just jump to the limit comparison test, because if I jump to the limit comparison test and it works, then I don't have to be like in this, okay, I'm pretty sure situation. So to do the limit comparison test, you take the limit as you go to infinity, and you do your a sub n divided by your b sub n, or your a sub n times the reciprocal of your b sub n. So I've got my 5 plus 2n over 1 plus n squared squared. And instead of dividing by 2 over n cubed, I'm going to multiply by n cubed over 2. And then I'll just rewrite this. And I'll distribute the n cubed through. So on top I get 5n cubed plus 2n to the 4th. And on the bottom, if I multiply the 2 through, and I think about like multiplying the 1 plus n squared times 1 plus n squared, this is going to give me 1 plus 2n squared plus n to the 4th, and then I'm going to multiply it all by 2. So down here I get 2 plus 4n squared plus 2n to the 4th. And then to solve this, you could do some L'Hopital's if you wanted to, but I like doing the shortcut where I divide everything by the highest power in the denominator. So if I divide everything by n to the 4th, that's going to make it so that these pieces end up going away. So this goes away, and all I have left then is 2 on top and 2 on bottom, which is just 1, which is greater than 0. So limit comparison test is going to work. So then if we look at what the limit comparison test tells us, it tells us as long as c is greater than 0 and it's finite, which this is, then either both the series are going to converge or diverge. So when you go back up and you look at this one here, this is just a p series with p equals 3. And when we think of a p series with p equals 3, that's greater than 1. So we know that this one is going to converge. So then we want to write that out. So how we would write that would be that we're taking this from 1 to infinity, and the 2 could sit out front, I suppose, just to keep it nice and simple. And this is a p series. P equals 3. And then you can say that it is convergent. And then you can say, therefore, our original series, so the given series, also converges. And I always say what test I used by the limit comparison test. Now, if the limit comparison test didn't work, I might go back and just assume that I know this, and it's like, okay, this one is, smaller than, and this one then converges, so the smaller one would also converge. So I think this would actually work by the comparison test also, so you might have used that. When I'm just unsure if one's larger or smaller than the other, sometimes I just jump to the limit comparison test and hope that that works so I don't have to kind of guess or feel uncertain about my answer. Okay, so the next one that I'm going to look at here is 27. And with 27, right away I looked at this and I was like, what am I going to compare that to? So when I'm not sure what I'm going to compare it to, I always think, okay, I probably want to compare it to a p series or a geometric series. And if I look at this part here, this is the same as 1 over e to the n. And sometimes people look at that and go, oh, that's a p-series. No, it's not. The exponent would be your p-value. So this isn't a p-series, but it's actually geometric. If you start plugging things into it, like if you plug 1 in, you get 1 over e. If you plug 2 in, you get 1 over e squared, and then 1 over e cubed. And you can see that you're always multiplying the denominator by e. So your common ratio here, this would be geometric, is 1 over e. So I like comparing it to this, because it's geometric with a common ratio of 1 over e. And then again, I can make my a sub n what's in there. And if I compare these two things, this part here matches exactly. So if I multiply it by this, it's going to get a little bit larger, depending on what my n value is, sometimes quite a bit larger. So as I'm comparing these two, I would say that my a sub n is going to be larger than my b sub n. And if I think about this being geometric, because I just want to see if this is going to work or if I have to jump to limit comparison test, as I think about my b sub n, I know this is about 1 over 3, and that's going to then be a geometric that converges. So if it's geometric and converges, if the smaller one converges, that doesn't tell us anything about the larger one. So the comparison test doesn't work here. So I am going to then try the limit comparison test, just like I did above. So I'm going to take the limit as we go to infinity. My a sub n goes on top. And my b sub n goes on bottom, which is just this. You could write it either way. And I can see these are going to cancel each other out. So now I'm just taking the limit as I go to infinity of 1 plus 1 over n squared. And as I go to infinity, this here is going to go to 0. So this just ends up equaling 1, which again, greater than 0. So my limit comparison test is going to be conclusive. Either both are going to converge or both are going to diverge. So now if I go ahead and I find what my b sub n is in here, I know that this is geometric. My r value is 1 over e, so therefore it's convergent. And then you can say, therefore, the given series is also convergent by the limit comparison test. And we're done with that one. And 31 I have seen on AP questions. I'm not going to guarantee it's going to be on the test in this class, but I'm not going to say it's not, because these often, with like the sign of 1 over n, for whatever reason, I feel like I've seen that several times. And these are like the I, double I, triple I ones where you have to be able to like come up with it pretty quick. So these, we're going to use a comparison test when you see something like sine of 1 over n or cosine of 1 over n or something like that. So I am going to just compare to what's in here. So my a sub n is that sine of 1 over n. And my b sub n is just 1 over n. Now, I know that this is just a p-series, p equals 1, divergent. But then if I try to compare these two, I don't know which one's necessarily larger than the other one. I might be able to figure it out if I like put them in my y1 or y2 in my calculator. But I can just use the limit comparison test again. And if I use the limit comparison test, I put my a sub n on top and my b sub n on bottom. And when I plug in infinity, I am getting the sine of 0, which is 0, over 0. So I can say, therefore, my L'Hopital's applies. And I'm going to make this even easier on my brain here. I'm going to take the derivative of the top. Derivative of sine is cosine. And then I'm just going to write here, then you take it times the derivative of 1 over n. Not that you can actually take the derivative, but what do you notice is going to happen on bottom? It's also going to be the derivative of 1 over n. So this is going to cancel this, and I don't even have to find the derivative then, but easy. It's an easy enough derivative to find, but if you notice something like that and the derivative is more complex, it's pretty easy to write it that way. Then I am going to plug in infinity. So this is going to end up saying cosine of 0. And cosine of 0 is 1. So greater than 0, finite, limit comparison test works. So now if I can figure out, which we already did, what the series here 1 over n is, this is a p series. P equals 1, so it is divergent. And limit comparison test says that either both converge or both diverge, so we can say, therefore, the given series diverges by the limit comparison test.